Question number 5. The question is about the structure and the bonding. 5.1 is an A1 question, which is a knowledge-based question, and student must have the knowledge about the structure and bonding of the carbon molecules. Figure number 5 represents the part of a carbon molecule. So this is a part of a carbon molecule, and this question is from graphene and fullerenes. Name the type of the carbon molecule in figure number 5. The name of this molecule is fullerene, and some students they write the word Buckminster a Buckfullerene, which is a wrong answer. It is a nanotube or it is a fullerene. So the correct answer is fullerene. Or carbon nanotubes. 5.2 is an application based question. Suggest one property that makes the carbon molecule in figure number 5 useful in nanotechnology. This topic is from the properties of fullerene. In figure number 5, the molecule is very useful. It is a good conductor of electricity. It is highly tensile strong. Tensile means that it is not going to break easily on applying the force. Its length to diameter ratio is high. If we see the ratio from the diameter to length, so the length is longer as compared to its diameter. We will say it has a high length to diameter ratio. Let's see the model answer. The molecule shown in figure number 5 is a carbon molecule of fullerene. It is a good conductor of electricity. It is highly tensile strong. It has high length to diameter ratio. 5.3. An alloy of aluminium contains small amount of other metals. Explain why other metals are added to aluminium. We will use this figure as a reference figure. We can see that in the pure metals, the particles of the metals are closely packed to each other. On applying the force, they can slide over each other. When we add the impurity atoms have different size as compared to the pure metal, so they will disturb the layers of the metal. As a result, these layers are distorted. On applying the force, they cannot slide over each other. This is the property which make the aluminium or any alloy stronger. Let's see the model answer. The other metal atoms are different in size than aluminium atom. If we consider this one is our aluminium and we added the impurity, the size of the atoms are different to the size of the aluminium atoms. These different size atoms will distort the layers of aluminum atoms. So these atoms they will disturb the layers of the atoms in the aluminium. Now aluminum atoms or particles are unable to slide each other. Before that, when we apply the force, they can slide over each other. But when we add the impurity, now there are no layers present, so they are unable to slide. This makes alloys harder than pure metal. So this thing is making them harder as compared to pure metal. Five point four is an A1 question. Figure number 6 represents part of the structure of a polymer. So we can see the polymer chain is present. So one chain is given here, second chain and third chain is given. Compare the bonding within the chain with the forces between the chains in the polymer. So this is one polymer. So within the polymer, the bond is present, that is called the covalent bond. And between the chains, the intermolecular force is present. These bonds are very strong as compared to the forces present between the molecules or between the chains. These forces or intermolecular forces are very weak as compared to the covalent bonds. So they need a little energy to break these intermolecular forces. But a large amount of energy is required to break the covalent bonding present between the molecules. Let's see the model answer. Within the polymer chain, a strong covalent bond is present between the monomers. Monomers mean one molecule. Between two polymer chains, the intermolecular forces of attraction are present. This is one chain and this is second chain. And between the chains, we can see that the intermolecular forces are present, which are shown with the red dotted lines. The covalent bonds within the polymers is very strong as compared to the intermolecular forces. So these bonds are very strong as compared to these intermolecular forces.